Hello, everybody. Welcome to another session of the Polkadot Deep Dives. And today we have a really nice topic prepared for you. It's called Try Runtime. Some of you may have heard of it. Others may not have heard of it. Either way, it's a critical piece as a frame developer, as a Polkadot developer. Try Runtime is crucial. So the agenda today, we're going to talk about like what is try runtime, what exactly is it, right? And uh, try runtime is I'll let you know that with my personal journey with try runtime, it wasn't the easiest thing to understand of like what it is. So I hope that with this presentation, we took all the complexity, at least we tried to take all the complexity out of it to present to you, to frame it in a simple way. Okay, so I hope that we achieve that. Please let me know. So we're going to discuss what is it. We're going to talk about some high level features. It's got a lot of features. We're also going to then drop down and actually talk about what's a typical flow, how it works. And then Bernardo has a deep dive demo for you set up where we're actually going to go through a try runtime example, which is really, really useful. Okay, and then at the end, we'll open it up for questions. By the way, my name is Bruno. If none of you know me, I'm a developer, an engineer at Parity, and Bernardo, which will be presenting the demo, is also an engineer at Parity. So let's get started. Try Runtime, Substrate's ultimate testing framework for the power users. That's a pretty hefty line. That's actually, I took that line from the documentation. It's at the very top. I can show you later. Um, it's a testing framework and it's ultimate. So that means there's a preface there, that little paragraph, that in order to really use try runtime, it's expected that you have somewhat of an understanding of the client and of the runtime. So how does the client work? Uh, how does the runtime work, right? What is the runtime? What is the client? What are the interactions between the client and the runtime and back and forth? Okay, so if you don't know what that is, I recommend there's great resources out there to understand the interactions there. Another prerequisite for this presentation and for really finding try runtime useful is to understand the upgrades, the runtime upgrades, how runtime upgrades work, perhaps even do a runtime upgrade yourself, as well as storage migrations. Okay, so these will be key elements to as part of the try runtime workflow. All right, so uh, what I want to do is we're going to look at a couple of definitions of try runtime and slowly get into it, slowly step into it. So the first definition here, it says the try runtime command line tool enables you to query a snapshot of runtime storage using in-memory externalities data structure to store state. With this tool, you can write tests against a snapshot of the runtime state before going to production. So I want to highlight here that it's a tool. In the previous slide, we said it's a framework. In this slide, we're saying it is a tool. All right. It's both a framework and it is a tool. There is a CLI. And this tool, you can think of it, it lets you, as a developer, as a frame developer, it lets you test your runtime in various ways. And it lets you test your runtime in detail with a high degree of control over the environment, the state, right? So let's look at one more definition. Try runtime is a CLI and a set of custom runtime APIs integrated in Substrate that allows you to do detailed testing, including running on runtime upgrade code of a new runtime on top of a real chain's data. Okay, I like how it says including there because there's more features that try runtime has, but this is one of the main features. Try runtime has a lot of features. We'll try to discuss like the top ones, and then we'll give you resources to go deeper if you'd like. But even here, like if we think about it, like why why would this be useful to test migrations for runtime upgrades, right? Let's think about that. Like if we think like what are we doing with migrations, right? Like what if a migration goes wrong, right? What can that lead to? That could lead to your chain stalling. That could lead to some unintentional consequences. So this is one of those pieces of like if you're writing a storage migration as part of your runtime upgrade, you want to make sure you test it properly. And there is no better way of testing it against actual real chain data, right? And try runtime allows you to do that. So a typical flow of like how try runtime works, you could say like pretty like hello world example here. It's like the idea is like step number one, you connect to a live chain. Step two, you scrape that chain's state and you put it inside of a test externality, which you can then use to call specific runtime APIs to test your runtime, to test did my migration, work as expected. All right. So this is really useful once again because you can rest assured that like you just ran your upgrade locally, you tested it against real chain data, and it worked. You have some checks in place to make sure, okay, this is my state before the upgrade, and this is my state after the upgrade, and they're aligned. This is what was expected, and that's a great reassurance. It helps you sleep at night because then when you push that upgrade to production, you've tested it, right? It's a great tool for that. So one thing that I want to mention is like the idea of taking state of a live chain and putting it inside of a test externality, right? If we think of state and substrate, we think of like key value pairs. And if we think, somebody said Polkadot devs don't sleep in the chat. Yeah, I can see that. Yeah. But if they do sleep, maybe they'll sleep better, right? The quality of sleep may be better here with try runtime. So when we're working with try runtime and we're taking state and we're pushing it into test externalities, we can actually pick what we want. We can pick the full state of the live chain, all the key value pairs, or if we want, like if that's not critical for what we're testing, we don't need all the state. We can pick specific pallets, the state from specific pallets or prefixes or keys. Okay, with try runtime, you're allowed to, you have that feature that you can select the key pieces of state that you'd like to go into test externalities. So a little recap here, a little review, right? We all know, like at least we should know if we're working with try runtime, that the client communicates with the runtime. How does the client communicate with the runtime? Via runtime APIs, right? And how does the runtime communicate with the client? Via host functions. So the runtime communicates with the client via host functions. And where is the storage? The storage is in the client, right? So if you're working with Substrate, you may know that the storage is in the client, and there's this thing called externalities. That's like, you can think of it as like an abstraction layer around the storage, around the data of your chain that's in the client. And the runtime accesses these host functions that are in the externalities, right? And so one example of this externality is test externalities. The idea is that we have this layer of test externalities that we can access that will have our live chain state that we can write unit tests against, essentially, right? I mean, that's pretty cool. Imagine like you're would try runtime, you could get Polkadot state or your parachain's live chain state and write unit tests against that state, right? That's pretty cool. how this happens, like under the hood, like you that under hood, there's something called remote externalities, which that's what takes the state of the live chain and injects it into test externalities. What you're seeing there on the screen, it's a code snippet. It's an example of how remote externality works under the hood and how you can use it. So you can see literally there that we're specifying like an RPC node there, Polkadot, and we're saying we only want specific pallets, the state of specific pallets. So in this case, pallet A, pallet B, pallet C, and some random prefix. All right. So this is going to be, an RPC request. So depending on the amount of state or what type of state you're getting, it could be slow. So, I mean, take that into account, right? You only want the state that you want to test against. Remote externalities is what allows you to specify the different pallets. You can, like mentioned in the previous slide, you can inject like custom keys. You could even inject custom key values. This is where you can kind of like customize like what kind of state you're going to be pulling in into your test externalities, right? So all of this coming together, we can say like with try runtime, the idea is that you download the state of you take the state of some live chain, perhaps Polkadot or your pair chain. And with the remote externalities, right, it will write that into a test externalities. So if we're testing some runtime upgrade, in this case, it'll overwrite the code, the well-known key called code, with some given wasm blob, the new one with the new changes, right? And then we can test that with some runtime API call, perhaps like something like unruntime upgrade, right? And we're testing it against real chain data. So for example, I keep saying testing, right? Before and after. So how you test like on runtime upgrade, right? On runtime upgrade is where you'd write your migration, right? So the migration, when you do the runtime upgrade, the migration will take place. With try runtime, there's two hooks that are pertinent to like on runtime upgrade. One is pre-upgrade, and you can see there on the screen. What's interesting about that code snippet is that there's a feature flag there. You can see it says the try runtime feature flag. So we're going to show you, but when you're enabling try runtime, these feature flags in the runtime get enabled. All right. So there's a pre-upgrade hook where you can run some checks on your state, on your blockchain, on your runtime before the upgrade. And then on runtime upgrade kicks off, does the migration, right? Does the upgrade. And then there's another hook called post upgrade where you do some checks after your upgrade, after your migration. And what's interesting, how these two hooks, they actually work together. I don't know if you noticed, but the first hook pre-upgrade, there's a result of vector U8, right? So it'll return some data, like whatever, logic you have in the pre-upgrade. It will run through that logic, and maybe you want to return some data. That data gets passed in as input to the post-upgrade. You can see there the parameter state vec-u8. So it's really useful for you to do like some check in the pre-upgrade, and then the result of that, you can pass it into post-upgrade to make sure that the state is consistent how you expected it. Okay. Try runtime also has some other features. We're not limited to like the unruntime upgrade, the pre-upgrade hooks, and the post-upgrade. There's also another hook that this would go inside of your pallet hooks inside of your pallet. It's called try state, and that hook can be used if you want to test that your pallet state is consistent and correct. So you can write some checks inside of try state. Other features that come with try runtime, there's some subcommands. You can see there it says on runtime upgrade. That's the one we just discussed. There's also another feature called execute block, which is really cool. The idea is that you could take a specific block, let's say, from the live chain, and you can execute it against your state, right? So depending on the use case, once again, there may be like multiple use cases here, but you can think maybe there was a block in the past that produced some type of bug based on the logic of your chain, right? And so you're pushing a runtime upgrade that should resolve that. So as part of your test, you want to test your upgrade against that block that created the bug, right? So you can use execute block. There's also off-chain worker. So that executes the off-chain worker hooks of a given block against the state that you specify. And the other one is follow chain, which is pretty cool. The idea there is that you're testing chain progression. So perhaps depending on your upgrade and your storage migration, you run your upgrade, you run your migration, and you just want to make sure that your chain is progressing as it should be. All right. And then that's where follow chain could be useful. It'll continue following the chain's finalized blocks and applying extrinsics. And that could be useful depending on your test case. So let's talk about a typical like try runtime, like a typical flow, right? Now that we know like some of the high level features, let's get a little bit more concrete and give you some steps of like how one would go about this. So step one, as we discussed, the idea would be you have some live chain, whether this be like Polkadot or your parachain, you have some live chain running, right? This is the chain that you want to scrape its state. And step two, you're going to write your migration, right? You got to write your storage migration. So we're going through a flow of like on runtime upgrade, right? This is the on runtime upgrade typical flow. So you have your storage migration, you wrote that down, it's in your runtime, the code is there. And you also have your checks in place, right? Your pre-hook and your post-hook. So you're going to do some check before the upgrade, before the migration, and then you're going to do some check after the upgrade, after the migration. You also want to make sure that you have some logs in place in your pre and your post, as well as in your migration, so that when you run your test, you can see the logs and all the important information that you want to see, that everything succeeded. The third step is you're going to compile that node that you scraped the chain data that you're going to compile the node that you script the chain data, but the one that you wrote your migration on. Okay. And you're going to compile it with the try runtime feature. So there's the line right there, cargo build -r features try runtime. And when you do that, you're going to get a binary with the try runtime CLI, the tool. Okay. That's going to be part of that. And when you compile a node with the feature try runtime enabled, all those feature flags that I mentioned that are in the runtime, the try runtime feature flags, they're going to be enabled. All right. So that's going to make it so the pre, the post, all those hooks that we discussed will be active. We then, after we've compiled that, we're going to take the binary, we're going to copy that binary that we just compiled. We're going to rename it to something like node try runtime because it's got the try runtime CLI in there. And it also has all the changes, right? The storage migration, the runtime upgrade, it has everything in there. So we're going to copy that and we're going to execute the binary with try runtime. So you can see there, I'm going to enable the Rust logs and I'm going to execute the node that I just compiled with the try runtime command. And I'm going to pass in the WASM that has the runtime upgrade and the storage migration and the checks. And I'm going to pass in the subcommand on runtime upgrade because that's what I'm testing. And with try runtime, you have to say checks pre and post so that those pre and post hooks will run. And then you specify the chain that you're going to scrape the data from. In this case, I'm using localhost because in this example, I have the live chain running locally. Okay. But this is where perhaps you'd have an RPC. All right. And RPC to Polkadot and RPC to your parachain. And you want to make sure on that side that you have RPC enabled on that node. And You may want to tweak the flags. There's certain flags that allow, how do you say, like, it may take some time to pull in that state. And you want to make sure that your node that has the RPC enabled doesn't time out. Okay. The specific flag, it's in the documentation. I can't remember right now on the top of my head. But then you execute this command, and that will execute the try runtime, and it will perform the upgrade with the storage migration. It'll run the pre-check before the upgrade, and it'll run the post-check after the upgrade. And it's going to tell you with green check marks whether it succeeded or not. And you're also going to get the logs that you wrote. Okay. So that's try runtime in a snapshot, in a nutshell. There are some additional features. I want to show you the documentation. So that first link there, it's really well documented. So perhaps I can show you that before we switch it off to Bernardo for a demo. There's also another talk there that I have listed at the end. And that's a YouTube talk, and it goes into try runtime, perhaps a little deeper on other aspects. So that might be interesting for you. But that's it in a nutshell. So let me just show you the doc. So this is the try runtime CLI in the Substrate Rust docs. I really recommend it. It's a great resource, and you can see it's got a lot of the information that we covered, and it's really thoroughly documented. So it's a great starting point to get started. And oh, here's the RPC flags that I mentioned. Okay. So there's some best practices, the pre and the post hook that we discussed, try state, checking state consistency. There's even some examples on there that you can test yourself. All right. So with that said, I'm going to hand it off to Bernardo for going over a demo. He prepared a demo for you. And hopefully with all this context, the demo will be super helpful for you. All right. Thank you.
Okay, so let's do a demo to give you guys a hands-on experience of how try runtime works in practice. We're going to do this on top of a substrate node template, which is a very basic substrate node. And we're doing a somewhat small modification to the runtime. That's so that you guys can understand the purpose of try runtime from very basic principles. So here we're simply changing the type of the balance. It used to be U128, and now we're using U64. And the implication of this is that the scale encoding of these balances is gonna change. So our runtime is interacting with storage, with the storage layer, and that's basically a key value database. And the values, all the values, they're encoded with Substrate's scale encoding. And by changing the type of the balance, we're changing the encoding of these balances. And we're using less bits. It used to be 128 bits, now we're using 64 bits, and that changes the encoding. And that basically means that the new runtime is incompatible with the previous runtime. And if we enact this change without properly migrating the storage, that is going to cause troubles because the new runtime won't be able to understand its own storage and all the balances that are there. So this line is pretty much everything that's being changed. This couple of other modifications are just so that we're able to compile this this code. And now we can sort of jump into some source code to see how storage migration looks like. So here we're on the runtime source code, right? Runtime source lib. And our main point that we should pay attention here is this, the migrate all accounts struct, and the fact that it implements the on runtime upgrade trait. So when we're implementing this trait, we have this function on runtime upgrade, and this is going to be triggered as soon as the runtime is being upgraded, right? It's going to execute even before the onInitialize hook. So what we're doing here is because we changed the balance type, that has some implications into how the accounts are being stored on the database, on the underlying storage database, right? So that is touching basically two pallets. That is the frame system and the balances pallets. Basically, balances pallet defines this account data struct, and that is used as a sort of a generic for the account info struct in the frame system palette. And frame system palette has this storage map called account, and that's where all the accounts live and all the balances live for the chain. So we're going over this storage map, and we're calling this translate function, which basically it iterates over every instance of the accounts in the map. And well, it is basically a key value pair, right? So we have access to the key and to the old value. We don't really care about the key, but we sort of care about the old value. And we have a closure here being passed inside this function. And this closure is simply creating a new value that resembles a lot like the old value. A lot of fields of this account info struct are the same, but the account data field is modified. It is translated, right? So we're basically taking the old value, but we're calling this saturated into, which is sort of a safe way to make this conversion, because we're avoiding overflows by using saturated into. This is coming from the fact that we have this saturated conversion trait in our scope, and by doing this, we're making a U64 from a U28, which is our main goal here on this storage migration. And we also have a simple counter here that, well, basically for every account that we're migrating, we're incrementing this counter, so we keep track of it, and we eventually print out a little log of how many accounts were migrated. So this is the gist of the runtime storage migration. This is going to happen right after the runtime is upgraded. So it's the first thing that ever happens in the first block with the new runtime. It happens even before the onInitialize hook, and it's going to convert all of our accounts from the old model with the old account data using 128 bits to the new model with 64 bits. And this function is returning a weight. And here I'm just returning 0 because I feel that benchmarking and weights are a little bit outside of the scope of this Polkadot Deep Dive session. But when doing this in production, you should have some knowledge on what benchmarks are, what weights are, and how to make sure that this is returning the correct weight, because this execution needs to be taken into account, and how much of the block of the initial runtime, the first block of the new runtime, how much of this block is being consumed by the storage migration. We need to take that into account. So ideally, we should be returning this weight here as the return of the onRuntime upgrade function. So this is how it is upgraded. And we have 2 extra functions here. And they're only used in the context of try runtime, right? This happens everywhere. This happens as soon as in production, right? As soon as the runtime is upgraded, this is gonna happen. These 2 functions, they only exist for the purpose of try runtime. And they're kind of a sanity check, right? That's the whole purpose of try runtime, is to do a sanity check on our upgrade and make sure that we're not breaking things and we're doing the migration properly. So what I wrote here is basically I'm iterating over all the accounts and I'm counting how many accounts there are, what is the total sum of their free balances, and then these 2 functions, they sort of communicate with each other by the fact that it returns a evacuate, the pre-upgrade returns evacuate, and post-upgrade receives evacuate, and these are the same, and they're encoded. We're encoding whatever we want to return here, and then we're decoding it here. So we're creating a tuple with the sum and the count, and then we decode it, and then we do the same thing. We iterate over all the accounts, we count how many there are, we do the sum of their free balances, and we're basically just doing a sanity check, right? Well, before my runtime upgrade, how many accounts there were, what was the sum of their balances, and what are those values for after the runtime upgrade? Are they equal? They should be equal. So we do this assertion here. And this is sort of a sanity check for our runtime upgrade that we're able to do because we have try runtime and we're building our node with the try runtime feature. So this is all the code that I had to show you. And going forward with the demo, I have 2 executables that I prepared here. One is called node template old, and it's basically a node without any modifications, right? It's the node template, it's running the old runtime, and it is synced with the chain. It has the current updated state of my chain. So it is here. I have it prepared on my machine, and it is running. This is what is running here on this side of the screen. It's basically the node template old already running and keeping track of the state of the chain. We also have a node template try runtime, which is nothing but a node built with the features try runtime, right? So we have try runtime available on this executable. And it's also here. I compiled it beforehand. We have 2 WASM blobs. They're both candidates for the new runtime. So both of them have these modifications here. They're both using the 64 bits version of the balance But one of them I compiled without the storage migration, and one of them I compiled with the storage migration. Both of them were compiled with the try runtime feature, but one of them is not the right way of doing it because there's no storage migration and we're sort of expecting things to break here. So if we come here and we execute this command, so here we are calling the node with the try runtime enabled, right? And we're giving it the try runtime subcommand. We're telling it to use, hey, we want to use the WASM blob without any storage migrations. We want to see what happens. And we're doing the on runtime upgrade subcommand, and we're giving it this parameter live URI, which is basically telling it, hey, when you're populating the remote externalities, I want you to look at this local node here and take the state from this local node. This could be perhaps some RPC node that just sitting somewhere in the internet, but well, having it on the same machine kind of makes things a little bit faster. So we execute it and we get a bunch of logs. The first few logs are remote externalities. So we're basically populating the state of our try runtime. And we can see here storage root. And we also have a few other logs here in regards to the spec version. The original spec version is 100. The new spec version is 101. And we also have a few debug logs here. And this is basically because when you're writing a storage migration, you could write it with two different strategies, right? Here, I'm writing it straight into the runtime. But I could have written it for a pallet, only in isolation, right? That wasn't my intention. This is a practice that's being sort of phased out here at Parity. We usually nowadays do it on a runtime level, but that is just for the context of these debug log lines here. They're kind of meaningless now because I didn't write any migration on a pallet level, and so we can safely ignore these lines. But for the sake of understanding, yeah, this means migrations that were written on a pallet level. So this line here, this is the most important line from this execution because we're using a WASM blob that had no storage migration on it. And then, as expected, we stumbled on an error that is an invalid state root. So the Merkle proof for our state, when it is calculated on the client level and when it is calculated after the block has been executed, they're different. And they're different because our new runtime is expecting to see balances encoded with U64 type. And that's not the case because we never migrated in any storage, and our balances are still encoded with U128. They're still encoded with 128 bits. And then when we are calculating the Merkle proof for our state, we get an incompatibility. And that's the whole point of try runtime. The fact that we are doing this on with try runtime and not on a production chain and not on the live chain, we can see that things would break if we do this runtime upgrade with this wasm blob, we were gonna break our production runtime. And well, we're happy. We should be happy that we have try runtime, because it enabled us, it allowed us to see that, okay, something must be done. This wasm blob is not ready. What do I need to do? And we also know the answer for that. We need to use the wasm blob with the storage migration. So this wasm blob was compiled with all this code here that I just showed you. And this time we're also giving it this checks parameter, just to make sure that try runtime is executing these two functions, this sort of a sanity check on our upgrade. And the rest is pretty much the same, right? So we're still pointing to the local node, and let's execute it and see what happens. So the first few logs, still the same thing, remote externalities populating the state of our chain. And we also have the spec versions, but now we have two new lines here that didn't happen before. So this first line here is happening during our migration. That is basically this line here. So we had our counter, and after we iterated over all our accounts, our counter looks like the number 4. And that is because, well, this is a node template, and I'm running it with the dev flag, and basically this is Alice, Alice stash, Bob, and Bob stash. So we only have 4 accounts in storage. And this line here is our sanity check on the post upgrade function. So remember that we iterated over all accounts. We also counted how many there are, and we made a sum of all the balances. So here we're printing that out, and this assertion, we assume it's passing because nothing broke here, right? There was no panic here. So this means that our storage migration was successful, because basically everyone that had an account before the runtime upgrade, they still have an account now, and their balances, they're still the same. Nothing changed, just how it is encoded under the hood. So that's it. We don't have any error messages. And now, because we did this with try runtime, we have a level of confidence that our runtime upgrade was correctly written. Our storage migration is doing its job. And when we decide to do this on our live chain, we're not going to break our live chain. So that's it for my demo.
Thank you all. Thank you for being a great audience, and looking forward to the next session.